In this video, we're going to look at the idea of vectors and how to represent them. Now, a vector is a geometric object. It's an object that has a magnitude, a size scale, let's say a speed or a force or a power or something, and it has a direction. So it has two quantities, a magnitude, how much, the size, the length of the vector, if you like, and it has a direction, and that's why we say it's a geometric object. So let's just start here with a vector in two-dimensional space. Okay, and we're going to start with something called a position vector. Position because it's anchored at the origin of some coordinate system, so x and y here, and we have our vector reaching out to this point here, x1, y1. And we can represent that vector v in a column format. So in the two-dimensional space, we will have this column format with the coordinates x1, y1. That's the coordinates of that point. That's where our vector goes to, from the origin to that point. Okay. In three-dimensional space, our position vector is represented v as x1, y1, z1 in these column format. Okay. We can also represent vectors in row format in this flat Euclidean space. Okay, and the magnitude of that vector now, the size, how much of it, its length, how fast it's going, or what have you, is modulus or magnitude of v is the square root of the sum of the squares of the coordinates. In two dimensions, it would be x1 squared plus y1 squared. In three dimensions, x1 squared plus y1 squared plus z1 squared. And in higher dimensions, there would be further coordinates added here, or the squares of those. Okay, so that's the basic introduction. That's how we represent it on a page. Let's just go down now. Let's just have a look at the process of physically adding and subtracting these geometric objects. So here's our vector u from point A to point B. Okay, and then our vector v goes from point B to point C, and the sum of those two vectors is then simply u plus v, which is here. So the final vector, u plus v, starts at the point A and finishes at the point C, okay? And we can represent that by AC with a half arrow above it. That's a vector going from A to C, pointing from the point A to the point C. And that's the sum of u plus v. To work out to subtract those two vectors, u and v, if we wanted to do, say, v minus u, then all we need to do is take the vector v, okay, and I'm just going to move it over here. Here's our vector v, like that. Let's put it all in. There you go, v. And to that, we're going to add the negative of u. Now, to take the negative of u, we simply move this one over here, and we flip it about the other way. Okay, the negative means pointing in the opposite direction, parallel to, but in the opposite direction. And that gives us then a resultant vector. Here we go, from v to u. Okay, and that is the sum of these two vectors, of the plus v minus u. Okay, v minus u. And geometrically, that's the process of adding and subtracting our vectors. Okay, I might just clear that up a bit. Okay, here we go. Now, let's move on. Okay, scalar multiplication. We're going to multiply by a scalar here. So let's say if our vector r has coordinates x, y, so we're in two dimensions again. But I mean, if we're in three dimensions, we'll add another coordinate below that. Then a constant k times r is equal to k times the x component, k times the y component. And if there are any more components, it'd be k times those. Remember, k is just a number. Okay, so is a vector k times r in magnitude, where k belongs to the real numbers. Okay, so k is just a real number here, and we're just multiplying. That's scalar multiplication. Parallel vectors. Now, if a and b are parallel, so vector a and vector b are parallel to each other, then a is simply k times b, where k, our scalar, is again a scalar, and that k can be greater than 1, in which case k times b is longer than the vector b. So here's our vector b, okay? And what that will mean is that vector a will point parallel to b, okay? Parallel to b in some way. But a might be, if k is greater than 1, if k is greater than 1, then this vector k times b will be longer than b, okay? And a will be pointing in the same direction. It will just simply be k times b, parallel to and the same size. If k is between 0 and 1, okay, then k times b will be smaller than b. If you look at that, okay, it's all these vectors are, vector b is all parallel to itself. All that's changing is just a constant. If k is negative, then it's going to point 180 degrees in the opposite direction. Okay, so if a and b are parallel, then a is simply k times b. Okay, that'll be the relationship between the two, because the magnitude of a doesn't have to be equal to the magnitude of b. Okay, but put the multiple k in, the scalar k in front, and it does become that. All right, next bit. Adding vectors. Let's have a look at an example here. Another way you're going to see vectors represented is in this row format. Let me get my pens back. You're going to see it in this row format here. Okay, that's another one that's acceptable in Euclidean space, but in other geometries they do, row and columns do have different meanings. But in flat Euclidean space we can represent them both the same way. And okay, so we've got vector v has coordinates 2, -5. Okay, vector w 1, 2. So if I look down here, here's w. Okay, I've got I've got a different w acting here, but anyway, not to worry. I seem to have a w that's 2, 2, but anyway, I could change that to 2, 2. All right, now, and vector v is 2, -5. So if I have a look down here, 2, -5, that certainly works. Okay, 2, -5. And what I want to do is, I want to find a vector pointing from v to w. V to w. Okay, so a vector from v to w, well, let's just pull them over here and play with them a little bit. Okay, v in the pointing towards w is going to be this long one up here. How do I get that? Well, what you can do is you can take the negative of v and add it on to w, and then what you get is a vector pointing in that direction. So if I just scroll down the page a bit, you should be able to see a diagram of that. Take w and add the negative of v to it. Okay, so w didn't change position. If I just go up a bit, w is still this one, 2, 2. Okay, and here it is. And then, but the negative of v, that's this one here. Okay, I'm going to reverse that by 180 degrees, so flip it around the other way, and then I'm going to add it on to the end of w, as is the normal process, and then that gives me w plus the negative of v is a vector from the origin to w minus a vector from the origin to v. Okay, and that gives me a vector from v to w. Okay, final, if you like, final. Okay, minus initial. Think of it that way. Final minus initial. Okay, v to w. Okay, final vector minus initial. All right. Let me clean up my space here a bit. Get rid of that. Gets a bit messy, but you can see here, w, add on the negative of v, and then what you get is a vector from v to w. Okay, and we represent that as v, w with a little half arrow above it. Okay, I think now one more section here. Let's look at some of the properties of vectors. Okay, the order in which we add vectors doesn't matter, and so the process is commutative. Adding of vectors is commutative. A plus b gives us the absolute same result as b plus a. Okay, it's associative because we can add a and b together, then add c, or we can add b and c first and then add a, and the end result is still the same. Okay, the zero vector, that's a vector 0 that has components 0, 0, and in 3 dimensions 0. However many dimensions you got, it's 0, 0, 0. Okay, the additive inverse is minus a. So if you take a vector and you take the negative of itself, add them together, you get the 0 vector. So that's the additive inverse. Negative a is the additive inverse. Distributive law applies. You've got some constant m or a function, some sort of scalar or something, you multiply it across m times the sum of the two vectors is the same as m times the individual vectors and then added. All right, so clean up that. All right, now A is parallel to B if there exists. Now you can say A is parallel to B if there exists some scalar k belongs to the real, excluding 0, because we don't want 0. A can't be parallel to 0 vector. 0 has no magnitude, no direction, so you can't say A is parallel to it. So A is parallel to B if there exists some constant k that belongs to the real, excluding 0, such that A is k times B. Okay, if A is just k times the B vector, then for some non-zero constant k, then they are parallel. Okay, now let's just have a look at another example. Now let's have a look at this cuboid. O, A, B, C, D, E, F, G. There's the corner points of this cuboid labelled. Is a cuboid, right? Let OA equal A, the vector A. So from O to A is the vector A. That's along the back wall there at the bottom. O to G, O to G, this vertical one here is the vector G, and then OC, okay, OC is the vector C, okay. You'll see what happens. Okay, so that we can represent the vector DC, that's a vector going from D to C, so we want diagonally from the top point D all the way across down to C. All right. Okay, and we can represent as the vector as D to A, plus A to B, plus B to C. Okay, see how we added those? Now, to do that, what we want then is D to A, if you remember, is the opposite direction of O to G. It's the negative of G, so we put minus G in there, because remember OG is just G. Let me just get rid of that. All right. Okay, A to B was our vector OC. Even though they're physically at different locations here, they're parallel to each other. We're free to move them about as we like, but A to B, this vector here, is the same as this O to G along here. O to C, sorry, O to C. Okay, so A to B is the same as O to C. We're free to shift them about in our space. All right. As long as we move them parallel to each other, they're still valid. We can move them anywhere we like on the page and perform the operation that we wish to perform. B to C here, okay, is the negative of O to A. So O to A went that way, and we defined that as plus A. So going the opposite way, backwards, will be minus A. And so we add these together. And that's the sum vector. That's the vector that takes us all the way from D to C. All right, another one. Just another point we need to make here, just to finish up now. If let's just say V equals 2 minus what 5, whoops, went too far there. Oh, nuisance. Okay, if V is 2 minus 5, 3, that's our vector, and the origin is 0, 0, 0, and so we're in three-dimensional space, and W is 1, 2, 6, find U such that VU is 2 times VW. Okay, now, let's just have a look here. Now, 2VW, that's a vector going from V to W, okay, means that we have 2 times the vector W minus the vector V. That's the vector. W minus V gives us a vector from V to W. I know that sounds odd, but you're actually going from, by taking the final minus the initial, you're going from the V to the W. You're getting the difference between the two, W minus V. Okay, so W is 1, 2, 6, and V is 2, negative 5, 3. There's a minus in the middle, so watch out for that. Okay, and what we have is 1 minus 2 is minus 1. We have 2 minus 5, that gives us plus 7. We have 6 minus 3 is 3. And then we have the scalar 2 in front, so we multiply each of the components by 2. So we get negative 2, 14, 6. And that's our vector, okay, 2VW. And that's equal to V to U, okay? Well, we can check that's equal to V to U. That's what we want to find. VU is OU, final, minus OV, initial, final, minus initial gives us a difference going from V to U. Okay, so that implies, if we just rearrange that, that implies that OU is VU minus OV. And so U, the vector U, or OU, is VU plus OV. So VU is that one, as we just discovered. Okay, and that's, and plus OV is this one. Remember, OV is the one we started at the top here. Okay, when we add those two together, we'll get 0,999. That's U. Now to check, VU is going to be the final vector, U, minus the initial vector V. That gives us our change from V to U. Okay, that takes us in the direction from V to U, final minus initial. Okay, always maths and science, we're looking at the final state minus the initial state. So we get U minus V. Okay, and when we perform this operation, 0 minus 2 is negative 2, 9 minus 5 is 14, 9 minus 3 is 6, and we see that negative 2, 14, 6 is the same as we discovered up here, 2VW, and which we claimed was that. Okay, and so we now find that VU is equal to 2VW as we found earlier, which was what we were after achieving. Okay, that's it then. Finished with that. I don't believe there's any more I had to cover here. No, that's it. Job done.